Hi everybody, this is Jazz from About Slingshot's YouTube channel. When we compare two Slingshot band sets, we make sure that either they are of the same thickness, as in this case, or we adjust the width of one of them in order to make their cross-sections equal, and only then we do the comparison test, such as here. But there might be some problems. First, for one producer of rubber, I heard that the rubber sheets were 0.60 millimeters thick, then 0.63, then some people measured even 0.67. And for me to measure the rubber sheet with a caliper is impossible. Maybe somebody can, but I cannot. Then from batch to batch, these thicknesses can be different for the same producer. And most importantly, the rubber bands do not have to have the same specific weight. So I think that equal cross-section approach is appropriate only for a special situation where we have known thicknesses and known densities. And I think that we need an approach which would transcend across all possible situations. In this video, I will present what I have on my mind. So this is how I approach the problem. I started with a well-known formula by which we calculate the exit velocity of the armor, and where we start with the draw power and we divide the draw power with armor weight, with pouch weight and the weight of the rubber itself in order to get acceleration. And then we add the final element, which is elongation, and which is, as you know, the difference between the total length and the active part of the bands. And then this yellow part is elongation, and this goes into the formula. So when we multiply these two elements, we get exit velocity. Then I said to myself, what if we have two band sets which we want to compare, and we make sure that they have the same weight of the rubber? And in my case, it will be, as you will see later, 3.71 grams. Same weight of the pouch, which is 1.08 grams. And the same ammo weight, which will be the steel ball of 8.731 millimeters or 2.73 grams. And then the same elongation, where the active part is 15 centimeters, stretch ratio of 5, which means that the total draw the draw length is 75 centimeters, where 75 centimeters minus these 15 centimeters of active band length, we get 60 centimeters of elongation, which then goes into this formula. Please note that here we do not speak about band thickness or band specific weight, simply speak of the rubber weight, same rubber weight under these conditions. And all we have to do is do the test and record the draw power and exit velocity. Let me show here my equipment which I use to make this test. Here I have luggage scale, which is connected to the automatic slingshot release. Then there are 3 slots for the stretch ratios of 4, 5 and 6, and I will be using only stretch ratio 5. Then there is a chrony, and there is a catch box, which basically is not much of a catch box. About 50% of the steel balls came back at me. There are some possible inconsistencies here in this equipment. Connection between luggage scale and automatic release was such that I had to wait a fraction of a second for the luggage scale to settle down and then do the firing. It is possible that there are some inconsistencies here between draw power and exit velocity, but I hope, and I'm sure actually, that all these inconsistencies are spread equally across all the shots which I will present later. So how I came to the same weight of the bands? I had at my disposal 2 rubber sheets. One I will call gold and the other black. They were of approximately the same size. Actually, I think they were 19 by 12 centimeters, but they don't have to be of this exact size. They can be of any. So I calculated their areas. Then I placed each of them on the precision scale. I got their weight. Then I divided their weight with the area, and I got how many grams there are in 1 square centimeter of each. And for gold, it was 0.0618 grams per square centimeter. For black, it was 0.0586 grams per square centimeter. And when I put these two values into the relation, I got that gold is heavier by 1 square centimeter than black by 5.51%. Then I arbitrarily said let gold be 20 millimeters wide. Then I multiply this number with this ratio, and I got that the black has to be 21.1 millimeters wide in order to have the same weight as the gold. And in final analysis, I got two bands, see, for each slingshot with 150 millimeters length each, gold 20 millimeters wide, black 21.1 millimeters wide. This is the weight per square centimeter for gold and the weight per square centimeter of black. And when everything is multiplied, I get that each of these band sets is 3.71 grams. Now, when we put these two band sets at test, if we detect any differences, what they can be attributed. Let me remind you, we have the same weight of the rubber, same pouch weight, same ammo weight, and same elongation. And what if the test shows, as will be the case later, you will see that one of them, in this case black, needs more draw power and has higher velocities than the gold. So to what this can be attributed? I do not know much about physics of rubber, but I found out that this can be traced back to retraction, contraction, and internal friction or internal characteristics of the rubber itself, which in turn can be attributed to material composition, manufacturing process, internal structure, and maybe more. So what shall I be comparing in my test? Well, generally, for any two or more band sets, we could test their performance on low and high temperatures, after how many shots they break, how they lose their draw power after 200, 500, 1000 shots, how they perform at low-high stretch ratio, how they perform with light-heavy ammo, and other. Here I test the velocity and draw power of these bands, but only at stretch ratio 5, only shooting one size steel ball of 8.731 millimeters, and only at elongation of 60 centimeters. Why? Because my primary objective here is to see how my approach works, and not so much to test these specific bands themselves. And this limited test should be, I think, just enough for that. And finally, how we are going to compare the results. We shall be using elementary statistics. 10 shots from gold and 10 shots from black will be fired, and draw power and exit velocity will be written down. Mean and standard deviation for both velocity and for draw power and some other statistics will be calculated in order to test the null hypothesis at 99% confidence level. Just to remind you, null hypothesis states in this case that there is no difference between band sets. And also a couple of possibly interesting ratios will be calculated. Results and conclusions. And here are the results of the test. These are shots number 1, 2, 3, 10. These are results for black bands, velocity, draw power of black, and for gold, velocity and draw power of gold. And here are some statistics. We are not going to go through all of them, but velocity of black is 73.6 meters per second. For gold is 60.6, which means that black is faster by 13 meters per second than gold. Also, the draw power of black is 5.1 kilos, and for gold is 4.293 kilos, which means that black is more powerful by 837 grams than gold. Finally, I have calculated here coefficient of variation, which basically tells us something about the variability within each of these series of data. And for velocity of black, it is only 0.89%, not even 1%. For gold, it is 2.8%, and this variability with gold is 3.2 times higher than with black. Also, the variability within draw power of black is 1.06%, and with gold it is 2.79, or variability within gold draw power is 2.6 higher than with black. However, the image will show, I think, these relations much better. You see, these are the data for black velocity and gold velocity, and it is visible that at every point of measurement, black is faster than gold. That is, there is no point where, for example, velocity of black drops down and the velocity of gold goes up and so on, so that they are mixed. And then you really need a statistical analysis sometimes to disentangle these two series to see if they are, as they say, from the same population or not. In this case, it's clearly visible that they are from two various populations, and also the variability within gold stands out in comparison to the variability within black. The same happens with draw power. At no point of measurement, gold and black come close to each other. Black always has a higher draw power than gold, and also it is visible that gold has some larger variability within its data. And finally, what does statistics say? I made the two sample t-tests, which says that the differences between average velocity for gold and for black are statistically significant at 99% confidence level. Therefore, null hypothesis that there is no difference between the bands is rejected. Or, in other words, the difference between them is statistically significant. This applies also to the differences in average draw power for gold and black. And I made some interesting, at least to me they were interesting ratios, but first I show you the symbols, which I will be using. This is draw power for black, draw power for gold, velocity for black, velocity for gold, rubber weight for black and rubber weight for gold. So first group of ratios looks like this. I took, as you can see here, the draw power of black and draw power of gold, and I got that the draw power of black is 21.5% stronger or higher than gold. Also, the velocity of black divided by velocity of gold tells us that velocity of black is 19.4% higher than gold. The other set of ratios looks maybe a little bit surprising. You see, the velocity of black is divided by the draw power of black, and it comes out that for each kilo of draw power of black there is 14.36 meters per second of velocity of black. But it's very close to what happens with the gold. You see, for each kilo of draw power of gold there is 14.11, which is not far from 14.36 meters per second. The third group of ratios I find most important, and I think that this is the clue for everything, for all other ratios that we have been reading and will be reading later. In this group of ratios I divided the draw power of black with rubber weight. It's rubber weight, and you remember in both cases we have 3.71 and 3.71 grams of rubber weight. So this ratio tells us that 1 gram of black rubber weight is responsible for 1.38 kilos of draw power. And with gold, it says that 1 gram of gold bands is responsible for 1.16 kilos of draw power of gold. And the final group of ratios, I think, is simply the consequence of this here group of ratios, which simply says that the velocity of black bands in relation to the rubber weight of gold bands is 19.84 meters per second, while with gold it is 16.33 meters per second. For me, for this limited test that I made, and for the data that we can read and try to do some comparisons and clues and so on, I think that this is the core ratio from which all other ratios stem. And it clearly says that 1 gram of rubber weight or 1 gram of rubber of black is more powerful than 1 gram of gold. Therefore, the velocities are higher, and so on and so on. Some comments. Black rubber, by each of its gram of mass, can absorb and release more energy. You simply need more draw power for black bands in order to stretch them to the same length as gold. This is evidenced by both a higher average draw power and higher average velocity. The surprisingly similar values for the ratio of velocity to draw power for both types of bends suggest that both types of bends are similarly efficient at converting energy into velocity. This implies that the key difference between these two types of bends lies in their ability to store energy during the draw, rather than their ability to convert that energy into velocity. So the recorded differences do point to the differences of material properties of the two types of rubber as we suspected in the beginning. I heard that gold bends were developed as resistant bends, while black ones were developed as slingshot bends. If that is the case, then gold bends are designed to provide a consistent level of resistance throughout their stretch. This is ideal for exercises where you want a steady force to work against. On the other hand, slingshot bends, like the black ones, are likely designed to store more energy, which would explain their superior performance in the test. And finally, one practical conclusion. If draw power is proportional to the width of the bends, then I guess that black bends should be only some 17.7 millimeters wide in order to have the same draw power as gold bends of 20 millimeters and similar velocity. You remember we had gold bends 20 millimeters wide, then we multiply it with the ratio of 1.0551 to get the necessary width for black bends, which is 21.1 millimeter, in order then to be of the same weight. But the results point to possible estimation that black bends, in order to be as powerful as gold bends, should be some 17.7 millimeters or 12% narrower than gold bends. But finally, this video is not so much about these two bends, although I have devoted so much attention to them. This video is about my approach. So, is my approach valid? Well, my approach was very limited. One ammo, one pouch and rubber weight and one elongation, but I think that it served the main purpose, which was to avoid lamentation and guesses about thicknesses and densities of the bends, and I think it did well. It was able to detect consistent data within each band set, but I must admit that any other approach would do the same if that approach had precise data of thickness and specific weight, which is not likely, and for this reason I said that the same cross-section area approach is valid only under special conditions. As the general conclusion, I say that rubber mass can be a good predictor of various phenomena when comparing slingshot bends. More than that I cannot say without further experiments, without your comments. So this ends this video and I hope you enjoyed. See you in my next video, most probably in Is There Something as Flat Trajectory After All, which is intended for novices. Please subscribe and thank you for watching.